Welcome to the Explainer. Today we are jumping straight into the ultimate insider's playbook for dominating differentiation. We're specifically targeting those tricky derivatives: e to the power of x, the natural log of x, sine x, cosine x, and tangent x for the Cambridge AS and A-Level Mathematics 9709 exam. So listen, there are generally two types of students sitting in that exam hall. Let's call them Alex and Sam. Now, Alex is the kind of student who overloads every single answer with raw mathematical facts, but provides, well, absolutely zero analytical structure. And then you have Sam. Sam rushes, completely panics under the time limit, and totally misses the command word requirements. I mean, Sam will calculate a gradient when the question explicitly asks for a stationary point. We are going to find the back door into every single question today. It's about working smarter, not harder, and completely avoiding those painful mistakes that trip up students exactly like Alex and Sam year after year. So I want to pose this really critical question right directly to you. Why do students find applying concepts to unfamiliar contexts so incredibly hard? I mean, you might know perfectly well that the derivative of sine x is cosine x, right? That's just basic rote memorization. But the absolute ultimate challenge of this exam is moving beyond that basic memory recall and into actual strategic application. Let's say you're thrown a complex real-world modeling scenario, okay? The displacement of a particle is given by some crazy equation combining e to the power of x and tangent x. Your brain literally shouldn't freeze. But Alex froze because, well, there wasn't a standard textbook example to follow. And Sam? Sam just rushed and differentiated the wrong term entirely. Understanding exactly how to bridge that gap between theory and application is what separates an average grade from an absolute top-tier mark. All right, here's our strategic roadmap. Section 1 is core principles. Section 2 is the method mark strategy. Section 3 covers the systematic processing framework. And finally, Section 4, examiner warnings. Let's get right into it. Starting off with Section 1, core principles, decoding the matrix. Okay, mastering differentiation is absolutely not about memorizing isolated rules. It requires a connected, conceptual understanding that effortlessly transfers to totally new contexts. Top students don't just solve math problems, they actively structure their answers using a framework. Think of it like a mathematical version of the Peel framework used in essays. The point is identifying the correct differentiation rule, like the product or quotient rule. The evidence is substituting your variables correctly. The explanation is your crystal clear step-by-step algebraic manipulation. And finally, the link is tying your final derivative right back to the specific context of the question. Examiners are actually grading you on 3 distinct cognitive domains: knowledge and understanding, practical application, and analysis with evidence-based reasoning. Imagine a scenario where you're differentiating y equals x squared times the natural log of x. If student A simply writes down the final answer with 0 working, and student B writes out, using product rule u equals x squared, v equals ln x, and then actively shows the step-by-step derivation, which one is actually demonstrating analysis? It's student B, obviously. Top-performing students always exhibit systematic analysis. They don't just jump to the finish line. They show the exact cognitive path they took to get there. Now, before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCS, to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Moving right along to Section 2, the method mark strategy. Let's see how Alex and Sam can finally start transforming those harsh red pen marks into green check marks. This brilliantly illustrates our core hacker mindset. The method mark strategy is all about earning guaranteed marks for demonstrating the correct problem-solving process and clear working, regardless of final answer errors. It is literally an insurance policy for your grade. Say you're differentiating y equals e to the power of 2x multiplied by cosine x. You correctly identify the product rule. Awesome. You write down your u and v variables, you find the individual derivatives correctly, and you plug them into the product rule formula flawlessly. But then, in the very last line of algebra, you drop a negative sign by accident. Look, you're going to lose the final accuracy mark, sure, but because you clearly showed your evidence-based reasoning, you will capture almost all the method marks for that question anyway. To make sure you nail those initial steps every time, I want to share a totally bulletproof memory hack. Because let's face it, under pressure, formulas can just vanish from your brain. So use a visual story method to encode these concepts. Picture this. E to the power of x is a stubborn boulder. No matter how hard you push it with differentiation, it doesn't change. It just remains e to the power of x. The natural log of x, ln x, that's a wood chipper. You put x in, and it gets chopped into a fraction, 1 over x. Sine x is a surfer riding a wave up to the peak of cosine x. And cosine x is at the peak, but falls down a negative hole to negative sine x. And tangent x? Tangent x is a firework that bursts into secant squared sparks. Visualizing this ridiculous story helps you securely encode and recall those complex rules when the clock is rapidly ticking down. All right, Section 3, Systematic Processing Framework. We are taking the utter chaos of an exam paper and turning it into a predictable step-by-step algorithm. Let's walk through this standardized sequence for flawlessly executing any differentiation problem. Step 1, identify key elements. Scan your equation. What exactly are you looking at? A composite function requiring the chain rule? Step 2, apply relevant principles. Actually write down the specific rule you are going to use. Step 3, execute analysis with clear working. Writing every single algebraic step. Step 4, verify results. Does this derivative actually make sense logically? And Step 5, present in appropriate format. Use the correct notation like dy by dx. Imagine a complex scenario, modeling population growth using p equals 5,000 times e to the power of 0.2t. Applying this exact 5-step framework completely eliminates the panic. You just systematically process the data, derive the function step by step, and extract those marks securely. Section 4, Examiner Insights, the traps. Even highly prepared students fail because they fall into specific traps highlighted year after year by the examiners. But hold on, stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to at acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. Okay, let's think like an examiner and figure out where things go wrong.
The absolutely crucial point here is that there are exactly 3 massive mistakes that cause students to needlessly bleed easy marks during this exam. If you can memorize these 3 warnings, you'll instantly place yourself ahead of like 80% of the candidates sitting in that room. Let's see what they are.
Straight from the principal examiner reports, here are the top 3 mistakes. Mistake number 1, forgetting to include proper format. Students will differentiate a function but leave it as this floating algebraic expression without ever writing dy by dx equals. It sounds minor, but you literally lose marks for it. Mistake number 2, failing to check format and presentation. This means sloppy handwriting where a minus sign looks like a smudge, or you're randomly confusing your x's and t's. Mistake number 3, providing answers not specific to the given context. And honestly, this is by far the biggest one. Let's zoom in on that third trap. The absolute classic mistake is providing a generic mathematical answer. Like if you just write, the derivative is 2 times cosine 2t, which means it goes up and down, that is purely generic. But a context-specific, mark-winning answer, that looks like this. The rate of change of the pendulum's displacement, modeled by the derivative dy by dt equals 2 times cosine 2t, indicates a maximum velocity of 2 meters per second at time t equals 0. Do you see the massive difference there? That second answer applies the correct mathematical terminology directly to the specific physical context of the scenario. That is exactly how you secure full marks for practical application. Section 5, Evaluation and Critical Analysis. This is where we separate the absolute best from the rest. Imagine a quick speed writing challenge. How would you write one perfect peel paragraph evaluating the nature of the stationary point for the curve y equals the natural log of x minus x? You would have to demonstrate true evaluative thinking, proving mathematically why it's a maximum or a minimum. The secret to totally nailing that kind of challenge is using the deconstruct, solve, evaluate method. This sequence guarantees a systematic approach when you face an unfamiliar question. First, deconstruct. Identify that you need the first derivative to find the stationary point, so dy by dx equals 1 over x minus 1. Second, solve. Break it down into logical steps. Set 1 over x minus 1 to 0, which means 1 over x equals 1, so x equals 1. Third, and this is the most important part, evaluate. Check for reasonableness. Find the second derivative, which is negative 1 over x squared. Substitute x equals 1 into that, and you get negative 1. Because it's negative, you know for sure it's a maximum turning point. See? You didn't just solve it, you evaluated the result and proved its mathematical nature.
Top-scoring candidates don't just stop at solving, they actively demonstrate evaluative thinking. They question the given assumptions. They consider different mathematical perspectives. They justify their decisions with hard algebraic evidence. And when they're asked to compare 2 models, say an exponential growth model using e to the power of x versus a standard linear model, they identify similarities and differences. They actively use comparative connectives like whereas or conversely, and they draw solid evidence-based conclusions about which model is more appropriate for long-term forecasting based on the exact derivatives they just calculated.
I really want to drive home this direct examiner alert because this is the ultimate golden rule to remember when you step into that examination room. Always link every point to the given scenario. If your calculus doesn't connect back to reality, you're bleeding marks. Now, students who implement these mathematics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos.
So here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to at acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for mathematics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here. Keep analyzing, keep practicing, and I will see you in the next explainer.